Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 50, and it is entitled Diverging Optical Elements, Convex Mirrors and Concave Lenses. These two topics are related to each other because both of them are going to produce images of a certain kind. We're going to see what those images are as we get to them. We will start with mirrors. Let's recall our work with concave mirrors. Suppose that I have a concave mirror, as in this diagram that's on the left, and I send in parallel rays of light that are incident onto the mirror. Maybe these are coming from the sun, which is essentially infinitely far away, so that all the rays of light come in parallel. At each point on the mirror, these 6 rays that I've selected out of the infinite number that strike the mirror form angles of incidence with respect to normal lines that have been sketched here. And what I would like to do is to show what the reflection of those rays are. So I'm going to take them one by one. The top ray looks like it has an angle of incidence of 19 degrees. In other words, I put a protractor there on the normal line and measured the angle of incidence, and so I constructed an angle of reflection that was 19 degrees. Now let's go to the second ray. The second ray made an angle of incidence of 11 degrees, and so I've constructed an angle of reflection that's also 11 degrees. We're going to work our way down to the third, fourth, fifth, and sixth ray and construct similar angles of reflection from these incident rays. The reflected rays from these incident rays are sketched here, and what I want you to see is that these reflected rays all come together at a single point. We call that the focal point of this concave mirror, and we call it a real focal point because parallel rays, the incident rays that are parallel, reflect and come together at this point, and they really do converge. When parallel incident rays strike a concave mirror, then their reflected rays really do come together. So we call this a converging mirror. Concave mirrors are known as converging mirrors because of what they do to incident parallel rays of light. Now, let's turn our attention to a convex mirror. A convex mirror has its reflecting surface away from the center of curvature instead of on the inner part of the sphere. If you think of the convex mirror as a section of a sphere, then the reflecting surface is on the outside of the sphere instead of on the inside. Or you can think of a convex mirror as an outie belly button if you want to. What happens to incident parallel rays of light when they strike a convex mirror? Well, let's play the same game that we did with the concave mirror, constructing reflected rays, and see what happens. So these incident rays on the convex mirror produce reflections that diverge. Those reflected rays don't really come together. But watch what happens if I trace backwards on those reflected rays. Those reflected rays behave as if they came from a single point, which is on the other side of the mirror. We're going to call this a virtual focal point. We call a convex mirror a diverging optical element because of what it does to incident parallel rays of light. The reflected rays from those parallel incident rays diverge. They would, if traced back on themselves, seem to have originated from a single point, the virtual focal point. What we want to do now is to figure out how to do ray tracing with such convex mirrors. And I have an example here. We're following the same rules of ray tracing that we did for concave mirrors, but now we have focal points and centers of curvature that are on the far side of a mirror instead of on the same side as the object. Remember, we have, of the infinite number of rays that come from the object, we choose rays that originate from the top of the object. We select 3 rays because they happen to obey the law of reflection in such a way that they're particularly easy to draw. So I'm selecting these 3 special rays. Let's review what they are and how we would construct a ray diagram using a convex mirror. First of all, we must, as we did with the concave mirror situation, sketch a plane of reflection. All of the reflections are going to be sketched from this plane of reflection, even though the curve of the mirror may not appear to be from there. The reason is that we're using something called a paraxial approximation. which means that all of the rays that reflect from the mirror are very close to the principal axis. In fact, the curvature may not show that, but for our purposes, we're going to sketch them this way because they produce nicer diagrams. The first ray leaves the top of the object and travels parallel to the principal axis. When this ray reflects, it reflects as if it had come from the focal point. But of course, it's going to reflect away from the mirror. So there are 2 points that I'm going to connect together. The place where the incident ray strikes the mirror and the focal point of the mirror, which is behind the mirror. I connect those 2 points together and then sketch the reflected ray as if it passed through the focal point, but of course it's going to reflect away from the mirror. Ray number 2. I think ray number 2 is the hardest ray to draw in these diagrams. To sketch ray number 2, you have to start at the top of the object and connect the top of the object to the focal point that's behind the mirror. So there's the top of the object, and there's the focal point that's behind the mirror. Ray number 2, the incident ray leaves the top of the object and travels as if it would pass through the focal point. Of course, the incident ray doesn't ever make it to the focal point because it hits the mirror first. When the incident ray reflects, it reflects parallel to the principal axis. Now we're ready for the third ray. For the third ray, the 2 points that I connect for the incident ray are the top of the object and the center of curvature of the mirror, which is on the far side. The incident ray is going to leave the top of the object and travel towards the mirror as if it would pass through the center of curvature. Because this ray that travels toward the center of curvature strikes the mirror at normal incidence, in other words, the angle of incidence is 0 degrees, then the reflected ray is also going to be 0 degrees, and so the reflected ray travels backwards on itself. So now the question is, where is the image? Well, we have 3 rays that have been reflected from the mirror, and those 3 rays diverge. Ray number 1, ray number 2, and ray number 3. The image is going to be located where the 3 of those rays intersect. And in order to figure out where they intersect, I'm going to have to trace backwards along the reflected rays. I'm going to use dashed lines to show this. There's ray number 1 traced backwards on itself. Now ray number 2, and finally ray number 3. Those 3 reflected rays appear to leave from the same point, which is right here. The tip of the image arrow is at that point. The tail of the image arrow sits on the principal axis. You should write the word image wherever those 3 words intersect with each other. And now we need to classify the image according to its nature, size, and orientation. The nature of this image is virtual, the size is reduced, the orientation is erect or upright. In these problems, you may be asked to sketch a scale diagram to locate the image and to measure the size or the height of the image. And that's how these problems are. So let's take a look at a particular example. An object 2 centimeters tall is placed 4 centimeters in front of a convex diverging mirror that has a radius of curvature of 6 centimeters. Use ray tracing to find the location, orientation, and height of the image. Is the image real or virtual? So we need to begin with a scale diagram. Now, I showed you a way to guide your thinking as you lay these diagrams out. I gave you a preview of a future lesson in which the lens equation or the mirror equation and the magnification equation appear. And it turns out that we can use those to help us make predictions about where the image is going to be and how tall the image is going to be. Let me remind you of those 2 equations. And again, this is a peek at a future lesson. In these equations, F stands for the focal length, SO stands for the object distance, SI is the image distance, HI is the image height, HO is the object height, C is the center of curvature. In this problem, they tell us the height of the object. The object height is 2 centimeters. They tell us the object distance. It's 4 centimeters. They tell us that we have a convex or a diverging mirror that has a radius of curvature of 6 centimeters. Now here's a special sign convention that we'll see later on. whenever we have diverging elements, it turns out if it's a diverging mirror, the center of curvature has a negative radius of curvature, so the focal length is also going to be a negative number. So the center of curvature is negative 6 centimeters. So in this problem, I find that the focal length is going to be negative 3 centimeters. So using the lens equation or the mirror equation, I can figure out what the image distance is going to be. So I solve the mirror equation for 1 over SI, and then I put in the numbers. I find that the reciprocal of the image distance is negative 7 over 12 centimeters. So SI is going to be negative 12 over 7 centimeters, or about negative 1.7 centimeters away from the mirror, on behind the mirror. How tall is the image going to be? Well, let's put those numbers into the magnification equation. So I solve for the image height, and now I'll put in the numbers, and now I'll put it into my calculator, and I find that theoretically the image is going to be just under 0.9 centimeters tall. Now that I know where the image is and how tall the image is going to be, I want to sketch a scale diagram of this, and I lay things out in such a way that I'll have these numbers that show me the characteristics of the image. So here's a scale drawing of this situation. I have an object which is on the left side of the mirror. It's 4 centimeters away from the mirror. I have the focal point indicated and the center of curvature indicated on the other side of the mirror. I've sketched the plane of reflection, and now we want to sketch our ray diagram. Ray number 1 leaves the top of the object and travels parallel to the principal axis until it gets to the reflecting plane. It reflects from that point as if the reflected ray originated from the focal point of the mirror. Ray number 2 leaves the top of the object and travels toward the mirror as if it's going to travel through the focal point. When it gets to the reflecting ray, it reflects parallel to the principal axis. Ray number 3 leaves the top of the object and travels as if it were going through the center of curvature of the mirror. It strikes the mirror and travels backwards along the incident ray. The reflected ray and the incident ray lie on top of each other. These 3 reflected rays diverge from the mirror, so I know the nature of this object is going to be virtual. Let me sketch backwards along the reflected rays and locate the image, and then classify its size and orientation. We have already calculated what its size is supposed to be, 0.86 centimeters, but let's actually sketch the reflected rays backwards and then measure graphically and see how close we come to that number. There's the first ray, reflected ray sketched backwards. Now for the second one, and now the third. You can see that those 3 reflected rays converge somewhere right about there. And so I'm going to make my image to appear right there. And you can see on this scale, it looks like that the image appears to be at about just shy of negative 2 centimeters. And we calculated before that we expected it to be at negative 1.71 centimeters. But if I were going to measure this graphically, I would say that the image distance is just shy of negative 2 centimeters. In terms of the image height, we're hoping for positive 0.86 centimeters. I would have to take my ruler and measure this. I get something on the order of about 0.75 centimeters, which is close to the calculated 0.86. In any case, the size is reduced, the orientation is erect or upright. My measured image distance, I'm going to say, is negative 1.9 centimeters. And my measured image height, I want to say, is 0.75 centimeters. When we get to doing these problems algebraically, you'll calculate exact answers just as we did when we were trying to locate and figure out the size of the image. But for now, these graphical measurements are close enough for our purposes. That ends the convex mirror.